So we're now recording. Okay. All right. So again, here we have some what do you call it? More examples. All right. So again, what we want to do for each of these, we want to draw the correspondence diagram. Okay. Not draw. Let me just fix that. Like that. There we go. Okay, we want to draw the correspondence diagram. And we also want to determine if it's a function or not. You can actually determine if it's a function by just looking at the relation, actually. Remember, what has to happen is you want all the ordered pairs to have different x coordinates. If that happens, then it's a function. So if we look at the first one, right? This is our first example. Here's the correspondence diagram, okay? And you can see we have the ordered pairs. Remember, the domain is all the x coordinates, as you can see, the x coordinates. So we have 1, 2, 3, okay? Then we have, that's the domain, right? I wrote it as a set. The range, that's all the y coordinates, as you can see as well. The y coordinates, okay? So we have 5, 12, and 20, all right? We have that. And now we have these arrows, right? So 1 would go to 5. That's what this arrow is telling us, okay? So that's what's happening. 2, 12, that's what's happening here, okay? We have 2 going to 12. Right? We have the ordered pair, so the arrow indicates that. 320, we have 3 over here, right? And the arrow goes from 3 to 20. You could think of a relation as almost like assigning, kind of like an assignment as well. I mean, it doesn't have to be a function, but 1 is assigned to 5, 2 is assigned to 12, 3 is assigned to 20. So again, the domain is all x coordinates. The range is all the y coordinates. Okay? And yes, this is a function. How do we know that? Well, there's really 2 ways of seeing it. From the correspondence diagram, right? What we have is from each input, only 1 arrow coming out of it. Only 1 arrow coming out of it. Okay? Meaning from each input, is assigned only 1 output. Remember, that has to happen in a function. Each input, you have to get only one output. And even without the correspondence diagram, if we go back to this, you can see that's going to happen in 1, right? All the ordered pairs have different x coordinates. And if they all have different x coordinates, you're going to have a function as well. You can probably see that in number 2, you don't get a function. I mean, the domain, it is a relation. A relation, remember, is just a collection of ordered pairs. So a relation, right? What we have then is, so we have a relation, excuse me. So from here, we have 5, 9, 5, 10. Excuse me, we have 5, 10, 15. So that's the domain. The domain, remember, is all the x coordinates. The range, remember, is all the y coordinates. So we have 9, 10, 7, 100. We have our correspondence diagram. So what we have then is the domain, each element in the first circle, the first set. The range, the elements of the range are in the second set. And remember, you're drawing these arrows, right? From your input to the output. Excuse me, from the x coordinate to the corresponding y coordinate. So in this case, 5, 9, we have an arrow from 5 to 9, excuse me. Here, we have an arrow from 5 to 10, as you can see. And really, we can actually see right away that this is not going to be a function, right? Mostly because, as I wrote here, well, just like I wrote here, we have two arrows coming out of 5. We have two arrows coming out of an input. Hence, we have an input and two different outputs. You know, in a function that doesn't happen. It's not supposed to happen. We also get this. In other words, we also can see this is not a function because we have two ordered pairs here, but their x coordinates are the same. So that also can't happen. So even without the correspondence diagram, we still can see that this is not a function. Again, 5, 9, and 5, 10 are there. So that's why it's not a function. Well, let's just finish the correspondence diagram. 10, 7 tells us we have an arrow from 10 to 7. We also have an arrow from 15 to 100 because this ordered pair is in there. So 10, 7, 15 to 100. So we finished the correspondence diagram. Okay. So this is not a function. You know, if you put 5 into this function, you know, which output are you going to take, 9 or 10? You have a choice, and you don't want that choice, so to say. Okay. All right. Let me just pause this. I want to make sure. Okay. This makes sense. Does this make sense? Does this? I really hope it is. Okay. I know before when I taught this, I did not go through correspondence diagrams, but I just think it makes it a lot easier when I use them. So, all right. I hope so. Okay, now let me stop there. For the third example, let me get the PowerPoint going again. For the third example, right? So even without the diagram, okay, is this going to be a function? Well, you should be able to see that the answer is yes. All the ordered pairs here have different x coordinates. Right? This is saying 2 is assigned to 8, 12 is assigned to 100, 4 is assigned to 2, 7 is assigned to 8, as you can see. Okay? So this is what happens here. So we do have a function here. And this confirmed it actually, right? From the correspondence diagram, you can see that each input only has one arrow coming out of it. I mean, here you have two different inputs with the same output. That can happen. That's okay. That is okay. So again, the domain is all the x coordinates, as you can see. Okay. And we have all the y coordinates here, as you can see. Good. All right, that's good. Okay, so we have that now. So we do have a function here. Okay. Okay, so we have these correspondence diagrams, we have relations, you know, we have different ways so far of defining a function. I think I actually mentioned it last time that we can use a graph to define a function. I mean, you should see that. You should immediately be thinking that because remember, a graph is nothing more than just a collection of ordered pairs, you know, points that is, plotted in the plane. That's all it is. So really, from any relation, you can get a graph. That's what the first sentence is saying. You know, if you remember, going back to our definition of what a graph is, it's just a collection of plotted points. That's all it is. And yes, you can go the other way around also. If I gave you a graph, you can come up with a relation. That is, you can list all the ordered pairs. Although you probably wouldn't want to do that because there could be infinitely many points. So you would be at your desk or writing for a long time, I guess. So you don't want to do that. What's nice is we don't have to. Now, just like there are relations that don't give you functions, right? We saw that. Not every graph will define a function. Okay, but how do we know which graph defines a function? Well, that's where this vertical line test comes into play. I mean, we will see some examples today, of course, but the vertical line test is basically how we can see if a graph gives us a function. What has to happen is, for the vertical line test, every vertical line you draw will either not intersect the graph or intersects the graph at most one time. That's when that happens, then we say the graph passes the vertical line test. In other words, the graph is the graph of a function. So again, every vertical line will either not, every vertical line is going to intersect the graph at most one time. So another way of saying that is you can't have a vertical line that intersects the graph twice or more. In that case, if it passes it satisfies the vertical line test. There's no vertical line intersecting the graph more than once, that intersects the graph more than once, then it's the graph of a function. Or if you want, you can think of it this way, it defines a function, namely in this case, every ordered pair looks like this. Every ordered pair looks like this. F is just what you call it. F is just denoting the function. You don't have to use the letter F, but usually that's what people use. That's what we're doing here. Let me just pause the recording.